So welcome to another Silicon Showcase interview for eFabless. And today I'm really happy to be joined by John Kustin. And John made this super cool bandgap circuit a little while ago. So we're going to look at what a bandgap is, how the circuit works, how the layout is, and then really importantly, the simulation and the results, because this design has been brought up and tested. So let me just bring on John. How's it going, John?
Hey, Matt. Doing well. It's great to be on here. Thank you.
Yeah, cool. Whereabouts are you based?
Currently, I'm in Ann Arbor, Michigan. I'm a PhD student here in Mike Flynn's group. And before that, I was at Stanford, and that's where I actually got the chance to do this bandgap project. Yep.
Okay.
The class with Priyanka Raina.
Great. And this was a class that taped out on the eFabless Chip Ignite shuttle a few years ago.
That's right. I think we might have been one of the first groups to actually get these designs on the shuttle. And It was a full class, a busy class. Yeah, excellent opportunity.
Great. Yeah. Is it, do many students get to do that? Was that for undergraduate, did you say?
It's listed as a graduate class.
Okay.
And in my opinion, if you figure out that integrated circuits is your path, or you're at least interested in it, then it's quite easy from a logistics standpoint to get all the way down the curriculum at Stanford for ICs. And so this was also like the quarter it was offered. This class was offered. I think it was still around COVID times. So had plenty of time, and at that point I didn't see any more undergrad grad distinction. It was just everyone was taping out,
Yeah. So I mentioned earlier that I've just done my first bandgap, but I actually found out it wasn't a bandgap. It was just a temperature compensated voltage reference. But while I was searching for publications or papers or previous work, that's when I found your repo. And
oh, great.
And I was like, oh, cool, this is on Sky 130, even better. And then even better, results are published. So I reached out, and we're going to have a talk about that now. So let me bring up the webpage. And for anyone watching, if you're interested in all the details, I'll link the repository down in the description below. So maybe we can start off just with, it's a bit further down here, like what is the bandgap, and how does it help you make a voltage reference you can use on a chip?
Sure. So I think very high level, right? You've got in this case these BJT transistors, and there's plenty of ways to actually make that in a process. But the idea is, if you assume a constant current, and then the only thing that's changing, let's say, is temperature, then you get a very linear looking change. And so, okay, you take control of that linear change, and then you generate an opposite kind of polarity to it, a positive and a negative. And somehow you sum these two changing quantities together such that when temperature does change, the positive changes cancel out the negative changes. And then you're left with a stable-ish voltage over temperature.
Just somebody turn the lights off in your lab.
Yeah, it looks like. Let's see some motion.
You got all right. Okay, you're going to be periodically waving. Cool.
I'll try to move around.
It's not that you're just like extremely excited about bandgap. Bandgaps.
Yeah, no, that was timed.
Yeah. Okay, so so the most things they have a positive correlation with temperature. So this is something that gives you a negative correlation with temperature. So the two things together cancel out.
That's right. The base, at least in this diagram, the top, there's this -2 millivolt per degree centigrade. And that's on the y-axis, it's the base emitter voltage. So across this BJT. So that has a negative coefficient, and then you generate something related to the actual thermal voltage, and that's how you get the positive one.
Okay, right. And if anyone is interested in all the details of what the bandgap voltage is and how that stuff works, even down to the quantum level, then check the video that I'm going to link in the top of the video here, either this side or that side, can never remember, by Projects in Flight. Really good video recently. Okay, so that's the kind of the basics. And then this is your schematic. So it's actually kind of a bit more complicated than I was expecting. So maybe we can see what the bandgap reference core is there. That's like those the two BJTs?
That's right. Those are the two BJTs. And the critical detail is that they're sized differently. There's a fixed ratio between the two. And without, recalling all the math, that multiple, I think it eventually is what lets you extract like a voltage from the two currents going into the two separate branches.
Okay. So yeah, one thing that I'm a complete beginner to the analog world here. I'm learning a lot this year. But one thing that I've found is that you can get ratios very, very precisely between transistors, but transistors across different dies or wafers can vary quite a lot. So is this an example of a circuit design that is made to depend on a ratio?
It is, exactly. Yeah. And I remember doing the layout. I guess we'll look at that a little bit later, that it's very critical to make that assumption of a ratiometric design. You're assuming that they change the same, but you can only make that assumption if the devices are right next to each other or very close to each other. So that was, I guess, like a detail that as a student, it didn't really connect with me until I had to place down the devices in the layout and like, okay, this is how we're able to make that assumption of ratiometric design.
Okay. And then we've got what looks like a op-amp circuit to me up on the left-hand side here. It looks like a fairly classic differential pair and current mirror.
Right. Yeah, that was a tricky part for me of starting out. This was like the first circuit I'd really ever designed. And the amplifier, from like a top-down view, it's doing a good job if the two voltages VA and VB are approximately the same. That condition it's in the derivation of like how this band gap works and what the output voltage is, that sort of thing. This VA equals VB is a critical assumption that you have to make. And in order to force those two voltages to be the same, you wrap feedback around it. And so in this case, like you said, this very classical differential pair input, single-ended output amplifier was worked enough for that. And I remember this is like while I had the chance, that there's good, positive feedback and negative feedback tidbit about this particular circuit, because I would say it's not really hooked up like a classic op-amp, because it's going right into this current mirror and then almost immediately back to the inputs. And at the top, so at the output of this amplifier, goes through that current mirror and back into the reference core. But the thing I want to point out is I think it's VA on that net, there's that capacitor. I think it's C2, and it's a pretty large one. And I don't know, the value. I think I just picked one that worked, as a novice, but it serves to to compensate that node. Because if you trace around that loop, VA to the input pair, to the output, through the current mirror and back, on that VA, I think that net has a positive feedback like sign if you to go through each transistor and kind of see, if a voltage increase at the input, does it decrease the output, that sort of thing. And so the main difference between VA and VB is that the sign with positive feedback should be compensated so that it's negative feedback that wins out overall, and it's negative feedback that allows us to force the error between VA and VB to be very small, very close to zero, And if that happens, then we should have a working band gap.
And that should work on another wafer with slightly different sized transistors.
Yeah. As long as all these devices are close to each other on that different wafer, you're good. And I think that's probably how people are able to make the claim that these circuits can be put into mass production and have high yield and that sort of thing.
Yeah. Okay. So then what's this current mirror or startup? Which one do you want to talk about first?
I think startup's an easy one. Because this circuit goes into real life and you have to turn the thing on, there's a pitfall in this particular topology of the bandgap reference. And that pitfall is you could enter a state, I think they call it in the literature like a degenerate state, but all the node voltages are at the supply voltage and you're stuck there because nothing is going to change and there's not really an input in this circuit. It's just an output. So if you don't handle the startup,
kick it into life.
Exactly, you have to kick it into life. And in this case, once you power on your like Caravan, Caravelle, wrapper, and the node voltages have all they've all charged up to VDD, and you're stuck at that point. So to get it into proper operation, that startup circuit, it's a single transistor. It pulls the gate voltage of the current mirror to close to ground. It perturbs the circuit, and that is enough of a kick for the feedback from the amplifier through the current mirror to lock itself into the desired operating point.
Cool.
Yeah.
I just designed a very simple oscillator with an op amp and a notch filter in a feedback loop.
Cool.
And had the same thing. It needed a kick to get it started. Yeah.
That was also tricky to set up in the simulations. The initial, do I need initial condition? Do I just skip? Should I see the whole progression from 0 to charge up to reset? It's challenging. Yeah. It's a beginner for sure.
Yeah. It's deep business.
Deep business indeed.
And then that current mirror, that's like, is that a kind of power supply for everything then?
I think in a way it's, I like to think of the current mirror in this, aside from sending a copy of the current back to the reference core. I guess starting with the current mirror that goes to the reference core. The point of that pair of mirrors is at like a quiescent point at the good point of negative feedback. Like what is the desired voltage at VA and VB, and what is the expected current that you designed to go through the BJTs. And so those two PMOS transistors are in the current mirror to facilitate that like DC operating point. And then the output, the final PMOS on the very right, that goes straight to a resistor. And that allows you to kind of decouple the current that you are like producing from the current mirror. And what I mean to say is the current going into nodes VA and VB, they don't have to be the same as the current that you see at the output. And if that's the case, then within some boundaries, and I think on this GitHub, there's more details about how to select that output resistor and what it does. But it allows you to change your desired reference
output voltage, right? Yeah,
exactly.
Okay, and then these resistors here in the bandgap reference, they're the ones that have the positive voltage slope.
Yeah, I think that's right. Yep, that's where you get one of your temperature coefficients from.
Yeah,
those resistors.
Okay. Yeah, that's this CTAT and PTAT.
Right.
Yeah. Okay. Cool. So I think that's good coverage of how the bandgap works in this particular schematic. Anything else you want to say about that, or should we move on to the layout?
I think if you're watching this video and you want to give this circuit a shot, just keep in the back of your head that there are multiple feedback loops in the circuit, and figure out which one is dominating, and then that may clear up some headache. And also this amplifier and self-bias, if you wanted to put your own spice into the circuit, then maybe modify the amplifier. Or the self-bias part is actually, if you look at the output of the amplifier, that first transistor, it mirrors the current down to the right, exactly, that mirrors it down back into the amplifier, and that's the self-biasing nature of this circuit. And you could imagine, if this is a reference with no true input except for the startup, then you'd want this to self-bias and start up on its own. But that's where the degenerate operating point actually comes from.
Okay. Cool. Okay, so is this something else, or is this?
It's a equivalent schematic, but it's more for layout. For doing,
okay, so it's like
LVS.
that. Those big resistors are replaced with 6 small ones.
Yep, unit. Yeah, as a student, I'm taught to use unit-sized devices and copy and paste those entire units rather than mess around with the sizes.
Yeah. Again, that's for better matching and performance across different process variations, right?
Exactly.
Okay, so then this is what you use, and does this include like dummies as well? Like these are dummy?
Exactly. Yeah, everything that is necessary to pass the final true LVS that would go through the tape-out process.
Okay, so these are all dummy resistors and transistors. Yeah,
exactly. And for anyone who might be wondering why I use these dummies in the layout, you imagine you have your circuit with no dummy, and then just look around the edges, right? Because you're not taking up the entire space. And if you were to imagine, I don't know, some deposition or like some etching, then right at the edge, there's a change between no circuit and then some circuit. And that circuit is your circuit. And that change on the silicon at that edge, there's, I don't know, I could wave my hands and say there's a discontinuity there. Whereas in the middle, picture in the middle of your circuit, it's been totally processed, and maybe you have multiple transistors next to each other. And so the point is, why use a dummy? You put a dummy at that maybe transition boundary between no circuit and your circuit. And what the dummy does is it allows the processing steps to perhaps, screw up a little bit on that edge because it's transitioning from different areas of the silicon. But because it's a dummy, it doesn't impact your circuit. And that was a very high level as a student, so maybe not the most technically accurate, but that's how it works in my head.
Yeah, that's now at the limit of my own analog layout experience. I haven't started using dummies yet. I'm just like, chuck the components on and hope it works.
The good thing is, I guess you're only limited by area.
Yeah. Okay, so then this is the layout in Caravan. So for people unfamiliar with eFabless Chip Ignite, there's a few different pad frames and contents you can have, and Caravan is the analog version of Caravelle. So it replaces some of the top I/O pins with basically bare metal pads for kind of high frequency or like high power stuff. But the essential thing here is, and I suppose an interesting thing is, like, look at all this empty area. Here's your bandgap, and all the rest of it is empty.
It's and there was a chance for me to integrate this project with it was a peers project. I think it was some boost converter, buck converter from Weston. But
is that Weston Braun?
Yeah, exactly.
Cool.
And so we were discussing, like, this would be he needs a voltage reference, I'm making one, so what if we combine efforts? But I thought, like, I was just so nervous about all the technical risk in this thing the first time. I'm like, I don't want to hitch my, wagon and then crash everything.
I know the feeling well.
But yeah, I look back at this and I'm like, man, I could have definitely put maybe copies of the circuit to try it out, a variation
like
on
variations theme. Or yeah.
Right. But there's really a good amount of working area in the through eFabless. They're awesome.
Yeah, 10 square millimeters. Okay, and then this is the kind of the main layout. So
right. I guess. Yeah, I look back at this and I could do it so much better.
What's that?
I'm looking back at this and I, kick myself. It could be so much better.
Yeah. So, well, that's interesting to know. So, your nice circuit diagram lets us understand. We've already seen these. So, these are the resistors and the JFETs. This is like that startup transistor. Here's the current mirrors. There's the kind of the amplifier and current source. Is that the output reference resistor?
On the bottom right, those are the BJTs.
Okay. Oh, that's actually the bandgap. Okay.
Yep, that is the active area for the bandgap. Yeah, and at the top of bandgap core, like where the text is overlaid, those are all resistors.
Those are all the resistors. Okay. Yeah. Right. Okay. So, I'm actually just starting to get a feel of kind of what looks like a good or a bad analog layout, but I'll let you tell us what you would do differently.
I think, well, there was in one of your older videos, I think somebody said if your layout looks symmetric across all, then that's a good sign. And so, I believe that is true. And so I'd look back at this, not very symmetric. Yeah. But I think as a beginner, that like the thing that I held closely, to my heart, to my brain, was I need to keep all like devices close to each other. And so that's why you don't see the BJTs spread out over area. They're all collected. But if I had to redo this, I would start all the way back from floor planning. And what I mean by that is from a high level, just like a PowerPoint diagram, where does the bandgap core go relative to the current mirror and the amplifier? Because as I did this with no real, foresight, I ended up having these very messy wires that, they go both in vertical and horizontal directions, maybe on the same layer. And that is not standard practice, and ended up leading to like I would say, in my opinion, a messy layout. But I was afforded that luxury through all that area and this shuttle that we were on. But
and is this your first layout? Your first manufacturing?
It was. Yeah. So got to start somewhere.
Yeah, exactly. Yeah.
I think there was actually this comes from PCB, some PCB experience. Like, let's say in my case, there's a particular chip that I want to test, and that is in the very center. Like the most important thing is in the center, and maybe applying that lesson to the circuit, to this layout, I would put the BJTs in the center and then work out from it to ensure that across any kind of gradient, like from lower left to top right, or any direction, that the processing, the etching might happen in, there's symmetry. There's something called a common centroid, and it's good to know what that is, but I think I wouldn't go for that style. I would just put the active BJTs in the center and then work out from there.
Okay, 140 by 220. Yeah, it's actually about the size of the analog slot, the smallest analog slots that we have on Tiny Tapeout. So we should maybe try a version of this on Tiny Tapeout sometime.
Perfect. Yeah. What's is there a maximum slot for analog on that?
It's twice that size.
Cool.
Yeah.
Yeah, and you could see there's plenty of just open silicon,
Yeah.
Free silicon.
And free silicon
could have been used.
Okay, so I think all right, and then we've got the simulation. Good to see these distributions happening. And here's your final specifications. That's how you know that you're not a complete amateur.
Yeah, yeah. Just half of one.
Intended and achieved. And this was exciting for me to see. Was like, oh wow, it's someone who's like set out with something in mind and then got the silicon back, measured it, and then has like achieved. I think that's really cool to have that published. And that was a big reason why I wanted to reach out to you and do this interview. So is there anything that you want to like talk about on this table? It looks like you beat your
Yeah, that temperature
PPMs.
coefficient, actually, that ppm is a thorn in my side because this number, that 3.6, is very low, like very competitively low, and it's not actually the temperature variation that I measured from the sample. This is a post layout simulation, and so I probably should have put that in the slides. But I think in some of the later plots of the measurements, I think it's more around like 100 parts per million. And that was once we discovered that temperature variation, and it was different than intended. We were curious, where was the discrepancy? And at that point, if I had, extra hours in the day, I would love to figure that out. It was just, I'm hoping that someone else can look at this design and maybe just leave a comment in the repository why it might be so different.
Yeah. Or if you can't be bothered to click on the GitHub link, then just leave a comment on the video.
Yeah. But everything else, it was just happy to fully characterize a real sample and to be able to publish that in GitHub.
Yeah. So let's maybe come up to my favorite picture.
Awesome.
I love this. So it's like, super hacky 3D printed with what looks like a Peltier effect device on the top there.
Yeah, exactly.
Coming down with some like copper standoff or something.
Yeah.
So that lets you control the temperature of the die.
Precisely. Yeah.
Okay. And then these wires coming out, was that like some kind of thermocouple?
Yeah, I think that's what would attach the thermocouple to like the driver for it.
Yeah. Okay. And then here we got the layout. Okay. Fan, PCB, function generator. Okay. Is there anything you want to mention about the test setup? Anything like that?
Yeah, for sure. The star ground is an important concept, I thought, and it was new to me. But because we talk about ground all the time in electrical engineering, but in this, just from this diagram, there's the supply, the function generator, and the scope. Those are three separate boxes. And maybe they're plugged into the same outlet, but probably not. And so star grounding.
Boxes? Oh, here we go. Here's the three separate boxes. Yeah.
Right. So we've got even three separate boxes supplying some kind of voltage, which is, always respect to ground. But we want to have precise, true measurements, and to really nail down what the ground is. We use the Caravel or Caravan board as that reference point. So all voltages are measured with respect to the ground that is created by that PCB.
And each one of these boxes plugs into the ground on that PCB rather than kind of in a chain.
That's right. Mm-hmm. And doing the cooling, anyone, I think I would be willing to bet money. Anyone who ever wants to test a device over temperature, they have their device under test, and they probably need some auxiliary circuitry or a microcontroller. Should be careful that everything that goes inside the chamber, the temperature chamber, hopefully it all works at the same temperature thresholds. Because if one thing, fails before your device under test, then you're out of luck. And I think that was what happened to me in this testing schema, where I wanted to go to a wider temperature range, but we were limited to what we could actually realize because of a microcontroller that was, we could have broken it. We pushed it too much.
Yeah. So let's move to one of your cool graphs then. This is the temperature from 10 to 65.
Right.
And then you see the slope, which is what you measured.
And that's the derivative. Yep, that slope is the temperature coefficient in ppm. Yep.
Okay. So and then you've got these 3 different loads. So 100 nanoamp load. It went from 0.94 volts up to 0.947 volts or something.
So I think I'm proud of this. It has at least a linear characteristic, which is we could work with that, if you wanted to.
I mean, I've been told that often, you still end up with something that's linear, but you can then program into the sensor or microcontroller, whatever it is, that needs to be calibrated out.
Yeah. So I think that's in like an AD data converter class, we're taught the same thing. Usually the linear errors you can just calibrate out later, which is cool. So I think though something that I learned about these 4 loads is if I had to redo this, I would think about, well, what's actually going to use this circuit? It was easy not to put an output stage, an output buffer. But when I put these 4 different load lines, it just felt a little weird that the load is so low, and maybe even, I'm not sure, maybe impractically low. This is where my experience ends, and I would defer to somebody, with more experience. But the intention was, if you want to use this device, I've shown you 4 loads, and hopefully you design your own buffer to work with this IP. But in hindsight, I probably should have included an output buffer to maintain these voltages across various loads.
Yeah. You've got to think about the next thing that's going to be connected on, right?
Yeah, I as a student, it's hard enough to wrap your head around the single circuit, and and even in analog design, I feel like this is a recurring challenge, at least for me. It's what is the spec? And ideally somebody gives you everything. But if you're working on your own project and you're well, I don't know what load to support. It's let, even in your mind, just create this, fake scenario of, this is going to go into it's going to set the common mode voltage for some amplifier, and maybe it's a bunch of amplifiers, and you use that assumption to come up with just, pull out a number. All you need is a starting point, and going from there to establish your own spec can help. It would help me realize a more robust design.
Although if you don't have a spec, then you can't fail.
Yeah, and that's if anyone asks me about this project, that's what I'm repeating internally to myself. I had no spec. This is just, if it worked, it worked. And that's good for students and stuff, but maybe not for the higher caliber clients of.
all the professionals that I talk to say the most important and the first part of the journey is coming up with a solid spec that everybody agrees on, because going back and realizing later that the spec wasn't correct and now you need to change it can impact months of work. So
totally relatable to this design process. For anyone who does their own bandgap, in this topology, you'll have to choose some current for each BJT, and then that'll create a lot of implications downstream. And so that kind of spec, if you have to change that, then you've got to change almost every size.
It's also interrelated.
Analog.
The voltage reference I did, I think there was 7 transistors. That was like by far the most active elements I've ever had in an ASIC analog design, and it was just mind-bendingly difficult to.
Yeah, even with 7, yeah.
Even with just 7, there's still like basically infinite numbers of combinations that they all affect each other, and everything is, it's really.
Yeah. That's actually the point that I'll tell my friends who are not in integrated circuits, and they're like, well, what is it really like? How would you describe the things that you do? And it's truly analog, at least in that sense. It feels like a puzzle, because just with 7, you've got this, messy, if you don't connect everything right, you've got a messy, intertangled web of just, stuff. But if you get the right combination and right sizings, then really like you've got something magical happening.
Yeah. Okay, so let's draw this to an end I'd just like to get your looking back on this as your first fabricated ASIC analog design. What do you think we've got there's a lot of interest at the moment in microelectronics and training and the various EU and US Chips Act. What's your take on students doing a tape out? Was this made an impact on you? Was it positive, negative? Would you recommend it for other students?
Absolutely. If you have the chance to do something like this, absolutely do it. It's rare. It's a privilege. Your design is able to be manufactured, and it's in the caliber of processes, of engineering processes, that is at the forefront of our capability. And that's just, as a student, a rare opportunity. And it was the first time for me that when the rubber met the road, all of this training as to be an engineer. And it was the first moment of validation that's okay, I can really do this. And on top of that, I really like it because it was such a challenge, but it had this immense payoff. So I really hope students listen to your YouTube, because it's a great entry point into this field. And any student out there, I don't even think you have to wait until college to do this kind of stuff, because the barrier to entry, everyone who is working in open source silicon, they're really doing an excellent job at lowering the barriers to entry. And in terms of preparing a workforce for the future, everybody knows if you start earlier and with more exposure, you're going to have more qualified candidates later. I feel like computer science did that too, and it was just easier for them, for all the reasons that have been discussed before. But now, if we have these robust shuttles for students to use, then you can, I think amortize is the right word, but you can amortize the cost of this, crazy silicon production across hundreds and maybe even thousands of students. And there's a lot about circuit design that is complicated, obviously, but there's also a fair amount that you can digest if they're taught well, on in an appropriate level. If it's approached correctly, I really think young people in high school, and I think that's already being done, can get themselves to a tape out. And I think the final thing is everything that these students will learn in college, if they decide to continue with ICs, it's going to be much easier if they started doing it in high school, and they already know what EDA tools are, and they already know I should save copies of my files in case I want to iterate on a design. All these analog tricks of the trade, you can start early. And I think it's a great recruiting tool. Absolutely. It's what made me decide to do a PhD, after this wrapped up, the bandgap. And it was I guess a success in my books. It was validation to keep going. So I think other people can use this opportunity to push themselves and discover a career.
Well said. Just one further question. How important do you think it is to take that final step and do tape out and do the measurement? Because it's normal that like, especially undergraduates, they'll do everything. They'll do the layout, they'll do the post layout simulation, but then that's where the project ends. How valuable is it to do the tape out, get the chips, and do the measurement?
I would say it should be required, and the reason why is, like if you're doing a math problem and you get it wrong, you always check your answer and you figure out what went wrong so you can correct it. And unless you measure your chip, you're not giving yourself that opportunity to discover errors and or bugs, and to improve upon something, or to correct it could be like your mistake, which might be repeated. So that being said, it's incredibly difficult to like test some of these things, some of these chips, maybe like depending on the precision and stuff. But with stuff like analog discovery or an ADALM from Analog Devices, like there are enough, I think, microcontrollers, stuff like that, to be able to test your chip. So really, like, if there's any student out there who's debating whether or not, I taped it out, no, that's cool enough, I'll put it on the resume and not measure it, you're really short selling yourself of like the value of what you did, because as an engineer, you eventually will get paid to make a product that works according to some specification. And if it doesn't meet the specification, then in the worst case, you might be fired. And so not testing, I think, sets up a bad like habit for students. And especially like if you want to do a graduate school in this, like you're going to have to test it. So I would not shy away with it. I would become comfortable with it, and as soon as possible, and figure out strategies to make the painful art of testing less painful.
That's a great place to leave it. So thanks a lot for your time, John, explaining the bandgap and your experience with the eFabless Chip Ignite.
Yeah, thanks, Matt. It's a real pleasure. Yeah, it's an excellent opportunity. And it's really cool to meet you too. Yeah.
Thank you.